right, hello everyone, welcome. In this new video series, I'm going to go over our practice project solutions, and we're going to start with the Chapter 9, Part 1 project on limits and derivatives, Part 1. Okay, for this one, we have a car sharing membership plan, $48 per month fee. This includes 12 hours of driving and then charges $9 for each additional hour. All right, so they give us some part of the piecewise function and we just need to find b. So for the second part, so the first part is actually the flat rate if you stay between 0 and 12 hours. But if you go over 12 hours, then you still need to pay the flat rate of 58, and then you have to pay $9 for each additional hour over 12. So that's why we subtract out the 12. So we can simplify this a little. And oops, this should be 108, right? 9 times 12 is 108. And so I get 9x minus 50. And so looking at this part, b is our intercept, which here is minus 50. So b is negative 50. All right, let's do a similar one. These types of questions, you'll get a random number to compute out of these three. I'll show you how to do all three of them just in case. But anyway, we have kind of similar, right? We have a f of x. It's going to be a piecewise. It's 56 per month, and it includes 10 hours. So if x is between 0 and 10 hours, then that's our rate. And then we charge $8 for each additional hour. So again, this part here is going to be our flat rate of 56 plus the $8 for additional hours over 10. So we'll subtract out 10 minus 80. So I get 8x minus 24. So this will be our second part of our piecewise. And this is for any x over 10. Okay, so for the first part, when we want to evaluate the limit coming from the right, if you visualize a number line like this, maybe more like this, right? We have a starting point of 0, then 10. So when x is between 0 and 10, it takes on this part of the function. And then when x is greater than 10, it takes on this part of the function. So when we're coming from the right towards 10, we want to look at the second part of the function. So this is going to be equal to the limit as x approaches 10 from the right of our second part of the piecewise function. So 8x minus 24. And what do we do with limits? We should always try to plug in the number and see if we get something reasonable. Sorry, that should be a 10. You write that better. And this gives me 56. All right, for number 2, let's see, for number 2, we're coming from the left this time. So this means as I'm approaching 10 from the left, I need to use this function, the first one, which is just 56. So that's kind of simple for us that there's no x involved. So no matter what my x is, I'm always going to be approaching 56. And then for the last one, you actually do have to compute 1 and 2, the left hand and the right hand limit, and see if they're equal. So since we already did the work, 1 and 2 are equal. So that our answer is going to be 56. Okay, so we now have volume discount. It's given by our volume in x and a discount amount. All right, so let's form our piecewise because it seems like we have different pieces happening. So, and these pieces are dictated by our volumes. So when X is between 300 and 1,000. Oops, not including 1,000. And then 1,000 to 3,500. 3,500 to 6,000. And then greater than 6,000. Let me space them a little more. All right. And then so all we need to do is define each of these pieces. So our discount amount, this is going to be the amount taken off of the total. So really we want to compute 1 minus the discount amount. So for the first one we want 0.021. So the discount amount is a percentage. So now we want to make it a decimal. And this is going to be 0.979, and we're going to multiply that by our volume, X. So it's pretty much the same kind of pattern. This will give me 0.96, so 0.96X. Next one is 0.075, so this will give me 0.925. 0.925x, and then my last one, 1 minus 0.104 is equal to 0.896, so 0.896x. All right, so again, we can kind of look at this like the last one. Here we want to approach 3,500, so now we're only really considered around 3,500, so to the left and right. So if you're coming from the right, we need to look at, right, you're coming from the right, so we need to look at the third part of the piecewise. So that was written really horribly. So this will be our third, this is our fourth. I guess I'll just write it all out. 1,000 and then 300s here. So our different pieces, if we just do it on a number line by volume. If we're coming from the right, I want to look at my third piece. So, oh, I'm doing the right. Sorry, I skipped a 2. So we want to find the limit as x goes to 3,500 from the right of my third piece of d of x, so 0.925x. And so you just plug it in, see what happens. And I got 3237.5. Let's see what happens when we go from the left. So when we approach 3,500 from the left, I want to be looking at my second component, or my second piece. So this is going to be limit as x goes to 3,500, and my second piece is this 0.96x. So again, let's plug it in, see what happens, and I get 3360. Okay, so those are the answers to 1 and 2. Now, if you got 3, you would need to do 1 and 2 in order to answer 3. Since these two are not equal, the limit does not exist. So it does not exist, and for the purpose of this quiz, you would enter 0 if it does not exist. So in your answer box, just put a 0. All right, average cost. So we have a snowboard manufacturing company, fixed costs of $208 per day, and total cost of $38.15 for a daily output of 17 boards. So a lot of information happening here. So we have this C of X. It's going to be our fixed cost plus some kind of variable cost, A times the amount of snowboards we produce. We don't know what that is yet, but that's okay, because we can use this second part of this prompt, that our total cost of $38.15 is equal to our cost of 17 boards. And so if we plug in 17 for x, we can solve for a. So 3815 equals 28 plus 17a. And then, yeah, you could simplify this a little and get 3815 minus 208. So this becomes 3607 is equal to 17a. Divide that by 17. And a comes out to be 212.176 maybe. So those are our variable costs. So we can plug that back into our cost function. 212.176x. All right. And then for the average cost per board, how it tends to go as production increases. So it's really what is my limit as x gets really large, goes out to infinity, of my average cost function. So to find average cost, we just divide our cost function by x. And you can do these individually. And it will be nice if you do it this way because look what happens. These x's cancel. So we get 208 over x plus 21, or 212.176. And so we want the limit as x goes to infinity of 208 over x plus 212.176. So if we plug in infinity, if we think about plugging in infinity, can't exactly do it, but you can think about it conceptually. 208 divided by infinity, which is a really, really large number, this will go to 0. Okay, so our limit actually is just this 212.176. And then we want to round to the nearest cent, so I'm going to make that 212.18. Okay. Alrighty, so for this one, we have a new employee can assemble n of t components. Okay, so we have this function n of t, and we want to find the limit as t goes to infinity of n of t. So if we plug in what we know about this problem, our n of t is this a, which our a is 147, t over t plus our b, which in this case is 9. And we want to see what the end behavior of this. So if we go ahead and plug in infinity, and I mean conceptually at least, we get this. We get basically infinity over infinity. All right, because the top is a really large number, the bottom will be a really large number. So the question is, which one's bigger? So when this happens, we can use our leading terms to decide what happens. So our leading term of the numerator is 147t, and the leading term of the denominator is t. So that's my variable with the highest degree. In this case, both have a highest degree of 1. All right. So this basically reduces down to the limit as t goes to infinity of 147t over t. And it behaves the same way for end behavior. And due to the cancellation laws, I can just cancel these t's. And so this limit goes to 147. Okay. Let's do a question about commission. Here we have a base salary of $9.89 per month and a commission on 5.8% on all sales over $10,000. If they sell more than 20,000 or more, they are given an additional $5.93. So I want some kind of piecewise E of S. Actually, let me write it down here. So E of S is this kind of piecewise function, and it's determined by how much sales, in this case S, we do. So if they do less than, so S is less than 10 or equal to, less than or equal to 10,000, then they get the flat base salary of $989. If they happen to do more than 10,000, but less than 20,000. This is a mess. Less than or equal to. Nope. Right? Because the last one is equal to, so 20,000. Right, and then the last one is if it's 20,000 or more. So X is greater than or equal to 20,000. So that's how this one should look. So what happens? So for $989, that's if you do less than or equal to $10,000. If you go over 10,000, you get the base salary plus the 0.058. That's our commission rate. And this is the amount of sales over 10,000. This is like the first few problems that we did. So we have to subtract out that 10,000. Let's simplify a little. S, and that is an S, minus 58, I think, right? And so this comes out to be 409, wait, 1, 2, 3, one more, 580. Okay, this comes out to be 409 plus 0.058 times this S. So S is our sales again. I guess these should be S's. Okay, and then the last one is we are adding 593 to this form if my S is over 20,000. Right, so let's just add that in. So 409 plus 593 is going to be 1,002. So their base or their fixed salary is just going to be this 1,002, and then we keep the variable the same. All right, so for this problem, we're looking at a few different parts. We have 10,000 and 20,000. So if you like the line approach, I guess they could also do a sales of 0, but probably not a big thing for us. So 20,000. Okay, so if I have these partitions, I know that my first part of my function is when my S is between 0 and 10,000. Second is when it's between 10,000 and 20,000. And then my third is the point after 20,000. So E of 1,000, or sorry, that's 10,000. This is just plugging it into our function where it's equal. So here we see that 10,000 is equal, but here it's greater than, so we're going to plug it into the first one. So if you plug it into 989, there's no variable, so it's going to be 989 regardless. So this one's going to be 989. Our limit as S goes to 10,000, that's going to be equal to the left-hand limit if it's equal to the right-hand limit. So we have to find this and this of E of S. So coming from the left, we have to use our first piece, 989. And then coming from the right, we're going to use our second piece. That's this 409 plus 0.58S. All right, so this is going to come out to 989. this one is going to be 409 plus 0.58, 508. Hold on. 0.058 s, so 409 plus 0.058 times this 10,000. And this comes out to be 989. Oh, that's great. So because these two are the same, our overall limit is 989. All right, for E of 20,000, we have to look at the piece where my S is equal to 20,000, so that's here, right? Not here, this is less than 20,000. Right, so we're just gonna plug it into that piece first. Let me just do some erasing. Okay, so E of 20,000 is equal to our third piece that we are considering, times 20,000. All right, and this should come out to 2162. So that's the amount of salary that the person receives if they did $20,000 in sales. Right, and for the last item here that you could potentially get, you want the limit as S goes to 2,000 of our E of S. So we need to find the left-hand limit. S goes to 2,000 from the left, 20,000. Limit as S goes to 20,000 from the right. So coming from the left, I need to look at my second piece. That's this 409 plus 0.058 S. And coming from the right, I need to look at my third piece, which is 1,002 plus 0.058 S. So again, just plug in those numbers and see what you get. 20,000. This comes out to be 1569. And then this one, we do 1,000, or 2 plus 0.058 times your 20,000. And this one comes out to be 2162. The difference is actually this additional amount that they get once they go over 20,000 in sales. So that's why there's a little bit of differential. So because these two are not equal, then our limit does not exist. And for the purpose of this quiz again, it's just put down 0 as your answer. Alrighty. So a few more questions. All right, so we have a graph. We want to check all the values where P is discontinuous. So I'm thinking this is a removable point. This is jump. So this occurs at T2 and T4. So the first two options. Now we want to consider the following values. So this one looks like it's around T1, T2, and T4. So let's see, let me put some number on the axes. Sorry, that's a 10. So each is 10, 30, 40, 60, 70, 80, 90. It's like so. All right, so that's kind of small, so maybe I can do that. So, so to answer part 1, you actually have to do parts 2 and 3 and see if they're equal. So let's do those first. Part 2, if we are coming from the left to T, that means I'm going to trace along the graph left to right. I reach this value 10. All right, and then for coming from the right, I need to trace along right to left, and I also reach 10. So because these are equal, my overall limit is 10. And then for the last part, if you happen to get this one, you need to know the function value, which it is defined, and it's also 10. And since these are all the same, that's means that we have continuity, which you can see from the graph. And anyway, question 9, we're looking at part T2. So again, I'm going to do parts 2 and 3 in order to answer 1. So coming from the left, tracing it, and I'm reaching 30. Oops, wrong one. 30. Coming from the right, going right to left, I'm also approaching 30. So the overall limit is also 30. But now let's look at what happens P of T2. So it's an open hole here, but it's been filled in down here. So that value is 10. So this is an example of discontinuity because all 4 of these are not equal. And you can verify that graphically. And last one, kind of same kind of method. I'm going to go from the left, and we're reaching 50. And then coming from the right, we're going towards 80. Because these are not equal, it's undefined, and so you should put down 0. And then the P of T4, so you have to look at where it's filled in, and it's actually up here, and so that value is 80. Okay? Alrighty. 2 more problems, let's do it. So we have this revenue function, and we want to find the average rate of change in revenue if the production changed from 954 to 1031. So this average rate of change, it's kind of like a slope where you would take, remember, like y2 minus y1 over x2 minus x1. So we can use our revenue to kind of produce these kinds of points. So if we plug in an input of 954 into our revenue, that's 67 times 954 minus 0.02 times 954 squared. This will come out to be 45,715.68. Now let's plug in our other point, or other input. 67 times 1031 minus 0.02 times 1031 squared. This comes out to be 47,817.78. So then these are our 2 forms, or our 2 points where we can put this one in the numerator. This is our output, so that's our y. Not use 715.68 minus, and then our other one, 817.78, all over our inputs. Just make sure they match. So the first one was 954, second one was 1031, and if you throw that into the calculator, you get 27.3. So 27.3. All right, for question 12, we want the derivative. That's just taking the derivative of 67. So that's going to be 67x. So that's going to be 67. And then minus 0.02 times 2x. So this really becomes 0.04. 04x. And so our derivative is this very last one. All right, and then 13, we want the instantaneous rate of change of revenue at the production level of 10,000 or 1,030 cars. So we're going to use our derivative and find the instantaneous rate of change at x equals 1,030. So 67 minus 0.04 times this 1,030. This comes out to be 25.8. For 14, we want, suppose production level is 1,008, compute the instantaneous rate of change, and then kind of interpret what this means for revenue. So our prime of 1,008, so again, plug it in to get the instantaneous rate of change. Oops. Okay, this gives me 26 26.68. Because this is positive, that means that my r is increasing. So r prime is positive, so r is increasing. So your answer should be 1 for increasing. All right, and for this last question, we have electricity consumption, and we want to build a quadratic regression equation for the data. So let me hop over to Desmos real quick and show you how to do that. All right, so let me first grab my data. Again, let's just copy and paste it in, just a little trick. All right, let's go back to the prompt real quick though, because it says that x is the time in years with x equals 0 corresponding to 2000. So just a little hiccup here. We just need to subtract out 2000. So the first one should be, just 0. 2003, that's 3 years from 2000. So again, just take 2000 off. And then 2012 is 12 years from 2000, and same for 2015, 15 years. And so we want to build a quadratic, so that's y1, use the tilde, ax1 squared plus bx1 plus c. All right, and for this question, we have to be careful with how we round our coefficients. So a is rounded to the nearest hundredth, b is rounded to the nearest tenth, and c is rounded to the nearest integer. So our model, once rounded, should be y equals a is to the nearest hundredth, so minus 2.08 x, and then our b is to the nearest decimals, or tenth, right? So 1 decimal place, 44.4 x. Sorry, this should be x squared because this is a quadratic, right? And then our constant is to the nearest integer, so 1185. Right, so that's the model we're going to use to answer the last few questions. All right, so again, our model that we got from Desmos is this, minus 2.08 x squared plus 44.4 x plus 1185. All right, so we need to use this regression model to predict the residential retail sale in 2024. All right, so again, remember that x is in time of years, with x equals 0 being 2000. So our x in this case is 24. So let's find our r of 24. So just plug in 24 wherever you see an x. All right, and this should come out to be 1,503. 1,053 billion of kilowatt hours. All right. And then for 16, we want to use the model to predict the instantaneous rate of change in the sale of electricity in 2020. So again, our x is 20 in this case, but now we want the instantaneous rate of change, which a rate of change should mean that we need the derivative. So let's take the derivative of r of x that we found from Desmos. So that's just going to be that using the power rule plus 44.4. Yep. And you can simplify a little further, get minus 4.16x plus 44.4, and then we just throw in 20 to find the instantaneous rate of change at 20. And this, I believe, comes out to be negative 39. So it's okay that it's negative again. because this is a rate of change, and the negative actually tells us that the sale is decreasing. So, and actually says, don't worry if your answer is negative. All right, so that sums up chapter 9, part 1. And I guess I'll see you at the next video for chapter 9, part 2.